Welcome, everyone. For today's prep, we're going to get our first taste of the derivative, but it's going to be kind of disguised. And what we're going to look at today is we're going to start investigating tangent lines. So let's just start with a quick review. So two of the basic gadgets that we're going to need when we talk about lines and tangent lines is we want to review how do we find the slope of the line connecting 2 points. So if we have 2 points P and Q, how do we figure out the slope of the line connecting them? Well, we take the y-coordinate of point Q, subtract off the y-coordinate of point P, and then we do the same thing for the x-coordinates, and we divide. So it's change in y divided by change in x. So you can remember this as really change in y over change in x. And the order really doesn't matter here. So if we had done y first and the y coordinates where we did point P first and then subtracted off the y coordinate of point Q, we'd get the same answer as long as we're consistent. So if we choose the y coordinate from point P first, then we have to use the x coordinate from point P first. So this is change in y over change in x. And if you want to abbreviate this, you could think of this as delta y over delta x. All right, so slope of a line. Now with that, it'll also be helpful to remember the point slope formula for finding the equation of a line. So this is for the equation. This is for just the slope. So there's kind of use these two equations a little bit differently. So this gives us the slope of a line, and then we can use the point slope formula to get the equation of a line. And what we have here is y minus the y coordinate of one of the points equal to the slope of our line times the times x minus the x coordinate of our point. So we have one specific point, and then we have our slope. And when we do this, the y here and the x here, those are actually just variables. So worth just kind of pointing that out. These are just variables. And then everything else, the y coordinate, m, and the x coordinate, those should all just be numbers. Okay. And then, we can simplify that and get it into y-intercept form. So a lot of times we'll get it into y equals mx plus b. So this will be the one a lot of times we start with, and then we can get it into this simplified format by solving for y. All right, so just a little bit of review for some important equations there. So let's get to the main kind of idea in what we're going to be investigating here. So when we talk about tangent lines, they usually come up in geometry when we're talking about circles. So it's possible to construct. So if we have a circle and we have a point P that we're interested in, it's possible to construct what we call the tangent line at point P. So this is a well-known geometric construction. We have our circle. All right, so this would be something you do in a geometry class. Now, what are some characteristics of this tangent line? Well, the important characteristics that we're going to keep in mind for when we kind of go to general curves and functions is this tangent line gives us a good approximation for what the circle looks like right around that point P. So if we were to zoom in on that point P, and that's what we're seeing here, you can tell that the actual circle and our tangent line, especially right in that section there, you can't really tell the two apart. They look very similar. So that's what we're seeing. So very close to point P, the tangent line should be giving us a good approximation to our circle. And then another characteristic that we want is the tangent line only touches the circle at point P. So it just barely kind of like grazes the edge of our circle here. Just touches it at one point. And that's going to be something we want with, some modification when we go to general curves. So it should just barely touch the circle. And a way to think of that is, again, if we kind of zoom in, imagine if there was a particle just kind of spinning around this circle. And imagine that as it got to point P, and it was kind of tethered, and as it got to point P, we just kind of cut it loose. And the tangent line is the direction that particle would just kind of keep going in, keep traveling in. So right around that point of tangency, the circle and the tangent line, they should have the same direction. So kind of the two things we're going to keep in mind is similar direction and good approximation. They should look alike. All right, so we're going to want to extend this to curves that are not just circles. So how do we do this? So the question is, how do we actually construct a tangent line for kind of a general graph of a function? And the difficulty is, so if we have a curve y equals f of x, so we have our curve right here, and then we have this point P that we're interested in, and we want to construct the tangent line. And the question is, how do we do that? Well, the construction is not as nice geometrically as it is with a circle. There's kind of a set way to do it with a circle. But for a general curve, on the surface here, it looks like there's not a similar type of strategy. And the idea here, and what we've been doing that's going to lead up to this, is, well, we kind of sneak up on our tangent line. So the idea is we're going to pick a point Q, kind of a second point on our curve, that's close to point P. And we draw this, what we call the secant line. So the secant line is going to go through our curve at those 2 points. And we can construct a line going through 2 points. So the difficult thing about constructing the tangent line is there's only 1 point that we know for sure is going to be on that line. So the difficulty here we only know 1 point. On the tangent line. Now with circles, we know where the center is, and there's things we can do. But for a general curve like this, we only know the one specific point. So, and we can't find a line without 2 points. So the question is, where does that second point come from? Well, we pick a second point that sits on our curve, and then the idea is we're going to imagine sliding that second point along the curve so that it gets closer and closer to point P. So let's see a little animation for how this would look. So bear with me for just 1 second here. You get a close-up of all right, so we've got our graph there. Let's slide this over a little further. All right, so you can see same graph we were looking at. And what we're going to do is we're going to let point Q move closer and closer to point P. And as that happens, we can see the secant line, starts to look more and more like what we want our tangent line to be. It has those properties. It just kind of grazes the edge of our curve, only intersecting our curve at 1 point right around that point P that we're interested in. And at point P, it looks like our curve and the tangent line there are kind of going in the same direction. So as point Q slides along the curve, the secant line starts to look more and more like what we want our tangent line to be. Now this is how it would look if we pick point Q to be on the right side of point P, but something similar works out if we pick point Q to be on the left side. And again, we can pick point Q on the left, draw a secant line, and then as that secant line, as point Q moves closer and closer to point P, the secant line starts to match up with our tangent line. Looks really nice. All right. So we're going to look at the slope process here, how we find the slope of our tangent line. We'll look at this in class. But first, let's figure out the slope of the secant line. So the slope of a secant line is, well, this is just our regular slope formula. So this is just the y-coordinate of point Q minus the y-coordinate of point P divided by the x-coordinate of point Q minus the x-coordinate of point P. And the way we find our y-coordinates is we plug the x-coordinate into our function. So let's try an example for calculating the slope of a secant line for the function y equals x squared. We have this point P that we're interested in with coordinates 1, 1, and we want to find the slope of the secant line when we have this other point Q with coordinates 2, 4. All right, so we want to find the slope of the line connecting points P and Q. So, well, it's change in y over change in x. So I'm going to start with my y-coordinate for point Q, which is 4, and then subtract off my y-coordinate from point P, which is 1. So I get 4 minus 1, and then in the denominator, we're going to subtract our x-coordinates. And when you do this, you just have to be careful. Since we started with the y-coordinate for point Q, we got to start with the x-coordinate from point Q, so we get 2 minus 1. And if we simplify this, we get 3 over 1, or just 3. All right. So let's try one more. Let's say we're calculating the slope of the secant line connecting points P and R, where R happens at x value 1.1. So first we have to figure out, well, what is the y-coordinate at that point? So to find the y-coordinate, we just have to plug our x-coordinate in to the function. Let's maybe rewrite that. So if we have our r value for point x, which is 1.1, and to get the y-coordinate for point r, we're just going to fill that in to our function. So our function here is x squared, so we're going to plug 1.1 into that, so we get 1.1 squared. And if we multiply that out, we end up with 1.21. So our y-coordinate for point R is 1.21, and then from there it's just the same change in y over change in x. So the slope for the line connecting points P and R, again, it's change in y over change in x. So our y-coordinate for point R is 1.21. Our y-coordinate for point P is 1. And then change in our x-coordinates. So this ends up being 0.21 over 0.1. And if we do the division there, we end up with 2.1. All right, so we'll get a little more practice with this in class, and we'll see, well, what happens as we move point Q closer and closer to P. We're going to end up doing a limit, so it'll be kind of fun. So we'll see you then. Bye-bye.